Bismillahirrahmanirrahim. Today we will start our lecture number 4. Lecture number 4 basically it is related with how elementary row operation applied to augmented matrix of a system of equations can be used first to determine whether the system is consistent, and second, if the system is consistent, to find all of its solutions. So we will learn different lemmas in this lecture in order to find out whether the system is consistent or the system is not consistent. If the system is consistent, so what type of the solution exists, whether infinite type of solution exists, whether unique solution exists. So also we will do in this lecture about different forms of augmented matrices. So let's start with one of the famous method called Gaussian elimination. The Gaussian elimination method. We now illustrate in this method how elementary row operations applied to the augmented matrix. So let's say, suppose this is example, determine the solution set to, you see three equations here. So we have to find the solution for these three equations. You see here, first equation is 3x1 minus 2x2 plus 2x3 equals to 9, x1 minus 2x2 plus x3 equal to 5, 2x1 minus x2 minus 2x3 equals to minus 1. So here we have a system of three equations and we have three variables also here. So first we write it in augmented matrix, that is our augmented matrix. 3 minus 2 are the coefficients from equation number 1. 3 minus 2 plus 2 is the coefficients, and right hand side value is 9. Then in next equation we have 1 minus 2 1, and on the right hand side we'll write here 5. Left hand side is 2 minus 1 minus 2. On the right hand side we must write here minus 1. So in order to convert in reduced echelon form, we first apply here permutation operation. We first tells us that swap or exchange row number 1 from row number 2. So here we write row number 1 as first row, 1 minus 2 1 5, and on row number 2 we write here 3 minus 2 2 9. So that is called permutation operation. First we apply. Now we by using that key element 1 as the leading one, we consider as leading one, and by using that leading one we must convert below 1 all zeros, right? So in order to convert below 1 all zeros, we must apply here two addition row operations. First we add row number 1 and row number 2, and similarly we add row number 1 with row number 3, right? So first we multiply row number 1 with minus 3 and add it to row number 2, that is called A12 by minus 3. So if you multiply minus 3, we obtain 0 4 minus 1 minus 6. Again if you multiply row number 1 by minus 2, so here you have minus 2 plus 4 minus 1 minus 2 minus 10. So if you add this row to row number 3, we will have 0 3 minus 4 minus 11. So why we are doing so? We want to convert that augmented matrix into reduced echelon form, right? So now we want to convert 4 as a leading one. So we have two options, whether we divide row number 2 by 4. So after dividing row number 2 by 4, we will have the fraction values in these two positions. In order to avoid this fraction values, we must add row number 2 and 3. So if you multiply row number 3 by minus 3 and add it to row number 2, we'll obtain 0, 1, 3, 5. And on third row we have leading one here. You see 0, 1, 3, 5. So you know it is the leading one on the second row. Now by using that leading one, we want to convert below 1 equal to 0. So we must multiply row number 1 by minus 3 and add it to row number 3. So if you multiply row number 2 by minus 3, you will have 0, minus 3, minus 9, minus 15. And add it to row number 3. So minus 3 plus 3 equals to 0. Plus 9 minus 4, minus 9 minus 4 equal minus 13. Similarly, minus 15 minus 11 equals to minus 26, right? So now we have this position 1, 0, 3 minus. In order to convert that minus 13 as a leading one, we multiply it by minus 1 upon 13. So if you multiply third row with minus 1 upon 13, so we'll have 0, 0, 1, 2, right? So that matrix, since it's satisfying all conditions of reduced echelon form, so you may say that is REF, reduced echelon form. So the system of equation, now we have x1 minus 2x2 plus x3 equal to 5, x2 plus 3x3 equal to 5, x3 equal to 2, which can be solved by back substitution. So if you substitute x3 equal to 2 in equation 2, so we will have x2 equals to 5 minus 6, that is minus 1. So similarly, if you substitute the value of x3 equals to 2 and x2 equal to minus 1 in equation number 1, we will obtain the value for x1. So here we have s equals to 1, minus 1, 2 is the solution set. So you see, first we convert the given augmented matrix into reduced echelon form. You see, that is the augmented matrix. We convert it into reduced echelon form, and then we write as equations which can be solved by backward substitution. So if we substitute it backward, we'll obtain the values for what? x1, x2 and x3. That these are the values. For x1 equals to 1, x2 equal to minus 1, and the value for x3 equals to 3, x3 equal to 2. So that is the solution set. So that method is known as Gaussian elimination method. Next method is Gauss-Jordan method. Again, in this method we illustrate how elementary row operations applied to the augmented matrix of a system of linear equations can be used to determine whether the system consistent and what should be its solution. So first we write that matrix into augmented matrix, that is the augmented matrix 1, 2, minus 1, 1, 2, 5, minus 1, 3, 1, 3, 2, 6. So that is the augmented matrix for this one. So in order to convert, here we have the leading one on the first position, first row and first column. You see, there is the leading one here. Now by using that leading one, we must convert below values equals to 0. So we multiply row number 1 by minus 2 and add it to row number 2. So after adding, we will have minus 2, minus 4, minus plus 2, minus 2. So if you add it to row number 2, we will have 0, 1, 1, 1. Similarly, in order to convert it equal to 0, we must multiply by row number 1 by minus 1 and add it to row number 3. We will have 0, 1, 3, 5. So again, we multiply row number 2 by minus 1 row number 2 by minus 1 and add it to row number 2, so we'll obtain 0, 0, 2, 4. And if you multiply row number 2 by minus 2 and add it to row number 1, we'll have 1, 0, minus 3, minus 1, right? So by using that row leading in order by using third row. First we convert third row into leading one row, so multiply it by 1 upon 2, so we'll have 0 0 1 2, and then we multiply it by 3 and add it to row number 1. We will obtain 1 0 0 5 0 1 0 minus 1 0 0 1 2, right? So that form is known as raw reduced echelon form. Raw reduced echelon form. So in that form we directly write the solution set, that is x1 equal to 5, x2 equal to minus 1, x3 equal to 2. That will be the solution set for the given system of equations. So that method is known as Gauss-Jordan method. And Gauss-Jordan method, you see, we convert that augmented matrix into reduced raw echelon form, that is reduced raw echelon form, by applying different raw operations, and then we must write it into system of equation, that is our system of equation x1 equal to 5, x2 equal to minus 1, x3 equal to 2. that will be our solution set. So what is the difference between these two methods? In Gaussian elimination method, we just find out the augmented matrix and then convert it into reduced echelon form, not raw reduced echelon form, that is called RF only, and then write it into system of equation and then substituting backward in order to get the solution set. That method was Gaussian elimination, but in Gauss-Jordan method we first find out its first we find out is augmented matrix, then by using elementary raw operations we must convert it into RF, raw reduced echelon form, and finally we obtain its solution set, that is x1 equal to 5, x2 equal to minus 1, x3 equals to 2. So consequently the given system has solution set 5 minus 1 2 in R3. Lemma. Consider the M cross N linear system Ax equal to B, where A is the coefficient matrix, X is the variable matrix, B is the right hand side constants. Then let A hash denote the augmented matrix of the system. So if the rank of coefficient matrix A equals to rank of augmented matrix A hash and both are equivalent to number of unknowns, so then the system has a unique solution, right? So in last example you may see that is RF, the rank of this matrix is 3. Rank of this matrix is 3. Coefficient matrix, you may see the rank of coefficient matrix is 3, and the rank of augmented matrix is also 3. The rank of augmented matrix is also 3, since both are equal to number of unknowns. The number of unknowns are 3. So since number of unknowns are equal to rank of the matrix of coefficient matrix equal to rank of the matrix of augmented matrix, so you may say you see here that matrix is coefficient matrix, and its rank is how many number of non-zero rows. Here you see how many number of non-zero rows, 3. The rank of that matrix is 3, and complete matrix, that is our complete matrix. So rank of complete matrix is also 3. So how many number of unknowns, you see that is x1, that is x2, that is x3. So how many unknowns here? There are 3 unknowns. So since rank of coefficient matrix is 3, rank of complete matrix is also 3, and number of unknowns is also 3. You see both all three values are equal. Since all three values are equal, we may say by this lemma that system has a unique solution. Similarly, if you apply that lemma in this example, if we first we convert this example, you see that matrix is reduced in echelon form since it's satisfying. So by lemma, that is coefficient matrix, you see its rank is 3, number of unknown rows is 3, and complete matrix, that is our complete matrix, so its rank is also 3. Since both are 3, you see both are 3, and number of unknowns is x1 minus x2 plus 2x3 is also equal to 3. That is the value of n. So is n equal to 3, and it is both are equivalent, n equal to 3 to the rank of coefficient matrix and the rank of complete matrix, all are 3, so that then the system has a unique solution. So that lemma tells us if the rank of coefficient matrix equal to rank of augmented matrix equals to n, we may say the system has a unique solution. Next example, determine the solution set to this system of x1 plus x2 minus x3 x4 equal to 1, 2x1 plus 3x2 plus x3 equal to 4, 3x1 plus 5x2 plus 3x3 minus x4 equal to 5. So here how many unknowns, and how many unknowns here? You see there are 4 unknowns. There are 4 unknowns for this matrix. So first we write that matrix into augmented form, that is our augmented form: 1 1 minus 1 1 1, 2 3 1 0 4, 3 5 3 minus 1 5. So here we have already a leading one. So by using that leading one, we must convert these two matrices equal to 0. So here we have to apply addition operation, that is our addition operation, elementary operation addition, and we must multiply row number 1 by minus 2 and multiply it to row number 2 and add it to row number 2, right? So that operation is known as addition operation. So if we multiply row number 1 by minus 2 plus 2 minus 2 minus 2 and add it to row number 2, so we'll have 0 1 3 minus 2 2. So again here we must find out the 0 element here, 0 value. So in order to get the 0 value, again we have to apply the addition operation, a, that is a using row number 1 and add it to row number 3. Symbolically it may be written like a13, and multiply row number 1 by minus 3 and add it to row number 3, will obtain 0 2 6 minus 4 2. So again using that leading one, that is our second row leading one, and using second row leading one we must find out 0 here. So again we using here addition operation, add addition, multiply row number 2 by minus 2 and add it to row number 3, will obtain this row. Okay, so finally we will have that form is called reduced echelon form. To check the rank of that coefficient matrix, what should be the rank? That is the coefficient matrix. So its rank is 2 or 3. You see it is the how many number of non-zero rows? There are only 2 non-zero rows. So you may say the rank of that matrix is equals to 2. Similarly, if you check the rank of complete matrix, that is our complete matrix here, so its rank of complete matrix is 3. So both ranks, since both ranks are not equal, rank of coefficient matrix is not equal to rank of augmented matrix, right? And these two values are not equal to n equal to 4, so system is not consistent because it does not satisfy these conditions. If rank of A is equal to rank, but in that example rank of A is not equal to rank of A hash. The system is inconsistent, hence system does not has a unique solution. So the last row tells us the system of equation has no solution, that is, it is inconsistent since it requires 0x1 plus 0x2 plus 0x3 plus 0x4 equal to -2, which is clearly impossible, right? Then the solution set to the system is thus the empty set phi, and hence you may say, since rank of coefficient matrix is not equal to or less than rank of augmented matrix, so then the system has system has no solution, or system is inconsistent, the lemma. So consider in last example, you see, consider since coefficient matrix rank is not less than augmented matrix rank, then the system is inconsistent, and that lemma also tells us that if rank of coefficient matrix is less than rank of augmented matrix, then the system is inconsistent and there does not exist any type of solution in this system. Example: determine the solution set 5x1 minus 6x2 plus x3 equals to 4, 2x1 minus 3x2 plus x3 equal to 1, 4x1 minus 3x2 minus x3 equal to 5. So again we first write that matrix into augmented matrix form, that is augmented matrix 5 to 4 minus 6 minus 3 minus 3 1 1 minus 1 4 1 5, right? So by using elementary row operation we want to convert these matrices into reduced echelon form. So first we add row number 1 to row number 3, so you may say that elementary row operation 1 may be written like that: A addition, A means addition, and addition of row number 3 to row number 1, and so which element we have to multiply by -1, since we want to subtract these two rows. So if we multiply row number 1, row number 3 is 4 minus 3, multiply it by -1, so we'll have -4 here. You see -4 plus 12 plus 1 and -5. So if you add it to row number 1, so it means 5 minus 4 is 1, minus 6 plus 2 plus 12, minus 6 plus 12 is -3, 1 plus 1 2, and -4, 4 minus 5 is -1. So that is our finally, after applying several elementary row operation, we will obtain here 1 0 0, -3 1 0, 2 minus 1 0, -1 1 1, 1 1 minus 1 1 0. So if you check here the rank, so that is our coefficient matrix, its rank is 2, since how many number of non-zero rows? 2, and rank of that complete matrix is also equal to 2, and number of unknowns is 3. Here n equals to 3, right? So since the rank of A is equal to rank of A hash, both are equal, so by lemma there exists a solution. But which type of solution there exists, whether it is a unique solution or whether it is not a unique solution. But you see here on first position, check which type of the augmented matrix is now in ref. Reduce is S1, x1 minus 3x2 plus 2x3 equal to minus 1, x2 minus x3 equal to minus 1, right? So the augmented matrix now in reduced echelon form, and the equivalent system is x1 minus 3x2 plus 2x3 minus 1, x2 minus x3 equal to 1. Since here we have how many variables? Since we have 3 variables but only 2 equations relating them, we are free to specify one of the variable arbitrarily. That is the methodology. Since leading one on the first position is 1, x1 position is 1, leading one on the x2 position is 1, but on x3 there does not exist leading one. So the variable that we choose to specify is called a free variable, or you may say x3, since does not exist a free leading one, so the x3 becomes a free variable here, and we suppose x3 equal to 2, x3 equal to t, right? So substitute it backward into second equation. So we will have x2 equal to 1 plus 3, and substituting the values of x2 and x3 in equation number 1, we will obtain the value for x1 lemma. So here one more thing, since which value we must put here. So t answer is that the t has infinite number of values. So if you put here infinite values, you will obtain infinite number of solution. So that type of solution is known as infinite number of solution. So it means if the system of the rank of augmented matrix is equal to 2 and the rank of coefficient is also equal to 2, both are equal, both must be equal, right? And both are less than number of unknowns. Here you see number of unknowns. So the system must have the infinite number of solution lemma. To consider the m cross n linear system Ax equal to b, let A hash denote the augmented matrix of the system, and let R hash rank of A hash augmented matrix. So if rank of augmented matrix equals to rank of coefficient matrix and both are less than number of unknowns, then the system has an infinite number of solution indexed by n minus R hash free variables. So you see in last example how many unknowns? 3. So n is 3, 3 minus 2 equals to 1. So how many free variables here? There are only one free variable, that is x3. x3 equals to t. You see, x3 equals to t. x3 equals to t. So that variable becomes the free variable. Since there does not exist leading one in these two equations, so it means x3 we will consider as the free variable. So by that lemma, last lemma, that lemma is to prove that if the number if the rank of augmented matrix is equal to rank of coefficient matrix and both are less than number of unknowns, the system has infinite number of solutions. Example: use Gaussian elimination method to solve x1 minus 2x2 plus 2x3 minus 4x4. So how many unknowns here? You see 4 unknowns. It is a system of 4 unknowns. The value of n equals to 4. You see 4. You see n equals to 4 here. N equal to how many number of unknowns? N equal to 4. You see that? Here you see number of unknowns, n equals to 4. So first we convert it into augmented matrix, and then we will find its solution. So if in this system has if this system has the rank equals to number of n unknowns, the exist system exponential. So this is assignment for you. You will try at home. So this will end our lecture number 4. In next lecture we will see further example related with system of equations. Thank you.